And good evening, everybody. We are live now. Sorry for the little delay. How are you doing, everyone? I hope you're doing fine. And here we are today on Twitch, and we will be welcoming in a few minutes Jorge Vago from ESA. But for the meantime, hello, everybody, and thank you so much for being here today. Thank you, Antoine. Thank you so much, Ezwak, for the support with the sub. Hello, Julienas. Hello, Loazo. Loazo will be our a special side guest tonight because she will actually draw some drawings during the evening, and I'll show them to you on the screen. So I can't wait. Also, the Loazo has been partnering with me for the last shows, and now we continue the partnership. I'm really glad, and thank you so much, Loazo, for the drawings this evening. Can't wait to see them. Hello, Sipa Queen, nice to meet you. Hello, Pauline. Hello, Nico. Hello, Le Geek. I hope everyone is doing okay. I'm doing very fine. Just a reminder for the true English speakers who are here today with us. I am not a native English speaker. There might be some times where I make mistakes in English tonight. English is not my mother tongue. I'm French. And thanks so much. Thank you so much, Robin. Thank you so much, Tous Comprend, that just landed with 17 people on board. Thank you so much for the red. And welcome, everybody. Tonight, sit down, relax, and we go on Mars. We've been talking a lot about Perseverance lately. Hello, Curie Noir. Hello, Tagazin. We've been talking a lot about Perseverance lately, but tonight, ladies and gentlemen, tonight requires I stand up to get energized, because we'll be talking about another Mars rover. Hello, Alice. We'll be talking about ESA Exomars rover that will be launched in 2022. Which is part of a larger mission which is called Exomars. Half of the mission is already in space with Exomars TGO. Hello Reset, hello Ben, hello everyone. And Exomars rover will be launched in 2022, and Jorge tonight will be talking about this rover, and maybe larger than that, about Mars and science on Mars, and what the rover will be aiming to discover. Just before I welcome Jorge on the floor, I just wanted to say, feel free to ask any questions. Again, feel free, even if you make mistakes in English in the chat, we don't care. I make mistakes all the time. So feel free, ask questions, and we will try to answer as much as we can. Thank you so much again for being here, and feel free also to take this opportunity to ask a question and discuss between you and also with the experts today. So with no further ado, I will just welcome Jorge on stage. Jorge, can you hear me?
Yes, very well, Corentin.
Hello, bonsoir à tous. Bonsoir, Jorge, and welcome in La Capsule. I'm very glad to welcome you tonight. How are you doing?
Very well, thank you.
Nice. Tonight, I just wanted to say that Jorge is seeing you the chat. You have an eye on the Twitch chat. Can you confirm?
I do.
Nice.
However, I have to say, I hear the volume twice.
Oh, so you can mute the Twitch, at the bottom left corner of the video.
Yeah, I've done that.
Is it better now?
Yeah, it's fine.
Nice. Perfect. So yeah, everybody in the chat is greeting you and welcoming you on stage. So we have a couple of hours in front of us tonight to discuss about Exomars mission. We'll be talking maybe a little bit about yourself in the beginning, just to introduce yourself to the community and speak about who you are and what are you doing today as an ESA project scientist. And then maybe we'll talk about the project itself and the Martian science and exploration. How does it sound like?
Sounds great.
Sounds great. Well, let's just start with how would you describe yourself, Jorge?
Okay. Let's see. I come from Argentina. I studied engineering in Argentina and planetary physics in the US. I came to the Netherlands to work at ESA in 1992. And I've been working on a number of things on the space station, on Russian capsules, on sounding rockets, and for the last almost 20 years on Exomars.
Okay.
So
You are a scientist, or have you been conducting some engineering work before joining the science team?
well, that's a good question. I'm actually both. And yes, at sometimes I've done work as scientist, and other times I've done work at systems engineer or project management.
Okay, yeah. I guess at this stage you have to understand both science and engineering, and we'll see tonight. But I think also Exomars is a very complex project where not only science team has to look to science objectives, but also has to bear in mind the technical and engineering constraints to build a proper rover and a system that lands on Mars in one piece, let's say. So yeah, I can't wait to speak about it with you. Okay, then we've been introduced. You are working in ESA for the last 20 years. Could you just
More.
a bit more?
Yeah, almost. It's closer to 30 than 20 now.
Wow, it's a very...
Yes.
As I see Lisa in the chat. Hello, Lisa. I just want to say hi to you. Lisa was with us 2 weeks ago now, or 1 week ago, when we did the YGT talk on this channel, which was the first English-speaking talk. So it's great. Already a first question from Benjamin. Wait, there are solar panels on Exomars. It isn't an LTG solution. No, it is not. It is solar powered, right?
Indeed. You have to think that the RTG on Curiosity and on Perseverance weighs by itself something in the order of, I can't remember exactly, but it's between 200 and 300 kilos. And that's the reason why you need a 1,000 kilo vehicle to carry that beast.
Yeah.
So Exomars is a bit over 300 kilos by itself. So if you have to get your power light, then you have to use solar panels.
Because how much Exomars rover weight in total?
It's today is about 310 kilos.
Okay, so we are like 1/3 of Curiosity's mass, right?
Right.
Yeah. So when we think about the mass they are able to land on Mars with their sky crane system, it really allowed them to land bigger vehicles on Mars.
Yeah, but it's tricky. I mean, the sky crane has to land something that weighs 1,000 kilos. It cannot land something that is lighter than that. I know because at a certain point we were thinking of using the sky crane to land the ExoMars rover. So we worked for almost 2 years with JPL to see what to do. And it turns out you cannot do it. So for a while we were looking at having sort of a pancake type of platform with two rovers, two smaller rovers, the ExoMars rover and an American rover side by side, and have the sky crane land that.
Okay.
In that way, we could get to the 1,000 kilos.
That's crazy that you are actually undersized from the landing point of view. Like you are too light to land. That's crazy. It's not usual in space related domain that we are too light for something, especially for landing on Mars.
Yeah, well, what it means is that you would have to reshape the capsule, make it smaller. You can try to use the same method, but it's not that evident that you can miniaturize everything, because the propulsion system that you need for guidance has a certain size. There are a number of systems you can make smaller, but others, they just
can't fit.
Get, tinier. Yeah.
And a very good question, a follow-up question on the use of solar-powered rover. Have you accounted for the dust covering the solar power? I know it's a problem on InSight for now. It has been a problem on several Mars missions so far. How will it be managed?
So the way we deal with it in Exomars is, okay, first I have to introduce another concept, which is the nominal mission duration. Mm-hmm. So when you make a rover, you specify in your contract with industry that you want it to work on Mars for X number of sols, which are the Martian days. In our case, that number is around 220 sols.
Okay.
So this means that the mission and the solar panels have to be sized in such a way that even under the, let's say, conservative dust accumulation conditions, and here conservative means you take the dust that accumulates per day to be as high as possible, by the end of the mission, you would still be in a working situation. Mm-hmm. Yeah. So basically, you have to make assumptions on what is the power loss you're going to have on average per sol, and you have to have a margin on that. Mm-hmm. And what I can tell you is that you always want to have bigger solar panels.
You don't have like a system to remove dust in any case? Or?
No, but crazily enough, we actually developed it and tested it in a Mars chamber and demonstrated that it could remove 99% of the dust on the solar panels. And still, we didn't use it.
But can you... Yeah, go on, sorry.
The reason is crazy. You see, the engineers, they look at a system like that. It was basically two big wiper blades that would move over the solar panels. And they said, the argument was like this: well, if you have this stuff and the motors fail, or one of the motors fail, then it's the same as not having it. So if we had it and we knew that we could clean the solar panels, we would make the solar panels smaller, because then we don't need them to be so big. We can clean them whenever they get dirty. True. But if the motor fails, that means you cannot clean anymore.
And you need them bigger.
And you need them bigger. So they said, we might as well not use them and just have bigger solar panels.
But you said you were
I'm not
using...
sure I agree with that line of reasoning, but that's the way it went.
You said you were planning on using two wind screens, like
yes, but they're not redundant. You just cannot wipe that entire surface with just one.
But I guess even if you achieve to wipe a little bit of surface, it gives you a little bit more power in a smaller area, which could compensate for the loss on a larger one, right?
True, but then the devil is in the details. And you see the rover has to unfold the solar panels. And at the moment, the outer ones, which you're sharing the image on the screen, right?
Yeah. Okay.
So the outer ones that you see there, they're actually folded over the fixed central one. And if you had to have the mechanism in between, it would have been a big complication.
Okay. Very interesting engineering topics, but we'll dive into science, which is more your subject of interest today. We have for you. We have made a plan. I'm currently speaking to the public right now. We have made a small plan for the presentation today. We'll go through a little bit of Martian history in terms of planetology and geology, and Jorge will highlight why Mars is of interest for the search of life, search of light. So we will highlight also the objectives of Exomars, which is clearly stated as searching for life traces on Mars, and we will see then at the end what is the status of the project and how the rover will actually hunt for life. But we have a proper presentation, and I think it's time to start going through it. So feel free to ask questions alongside, and we'll go through. We also will try to manage the time, because it is quite a dense presentation. So let's just start right now, I guess, if you agree, Jorge. If it's that. Okay, I'm currently displaying the first slide, and feel free to tell me to go forward or backwards. No problem for me.
Okay, then let's go to the next slide, please.
Yes. Okay.
So we will discuss a bit about the early evolution of the terrestrial planets in the solar system. And by terrestrial planets, I mean Venus, Earth, and Mars. So initially, these planets formed through a process of accretion that starts with very tenuous dust aggregates that come together and start to attach to each other and form these sort of fluffy balls. And as they encounter more and more of this material, they start to grow and they become denser. Eventually, you start having planetesimals. By planetesimals, I mean objects in the size in the order of a meter or so. When objects start to get bigger, they start to see each other gravitationally. As they come closer, they may perturb each other's orbit a little bit. Be that as it may, this process keeps on going until you start having objects that are chunky in size. So let's say hundreds of meters in size, a kilometer in size. At that point, most of the material, every time that comes into contact with another object gravitationally, will get ejected in some strange direction. Many of these objects will collide. By the time you have denser clumps, they have a higher gravitational mass, and as they sweep their orbit around the young sun, they basically start sucking in like a vacuum cleaner material. Mm-hmm. And you can imagine that this is when the objects start getting bigger, it's a pretty violent process. If we move to the next slide, please.
Yeah, sure.
So eventually, you will get what are called planetary embryos. And these are objects that say the size of a moon. The early solar system had many, and most of them were lost into space. Some fell into the sun. A few of them collided and grew into what today are the terrestrial planets. But this was a super violent process. So initially, the terrestrial planets were giant balls of molten magma. They were so hot that even the rock was fused, which is a bit of what you see here. Now, the planets started to lose their heat to space, and the solidification process, bizarrely enough, proceeds from inside out. And as the planet mantle starts to solidify, let's say cool and then solidify, it cannot hold in solution the same amount of gases that it did when it was at very high temperature. And so what happens is that within this magma that is becoming colder and colder, the gas that is dissolved starts to bubble up. And if we go to the next slide,
yep. Volcanoes.
You would have seen if you could have walked on the surface, actually you wouldn't have seen anything, because it would have been so full of steam and other gases that it would have been very difficult to see anything. But in essence, it would have been molten rock with bits of scum floating here and there, and a lot of energy. If we go to the next slide.
Sure.
This outgassing of the mantle and the crust as they cool down produced the primordial atmospheres. And the primordial atmospheres were composed mainly of CO2, water, and nitrogen. And the amount of atmosphere that was outgassed was so much that they were supercritical. What does it mean, supercritical? Supercritical state is one in which a fluid doesn't know whether it should be a gas or a liquid. Imagine a gas. The molecules are freely moving everywhere, but now you increase the pressure. And you increase the pressure so much that even though the temperature is, for example, let's say 300 degrees, and water would like to be a gas, the pressure is so large that it's actually forcing the atoms or the molecules to behave as a liquid. And this is what is called a supercritical state. The atmosphere of Venus today is supercritical.
Okay.
But take, for example, the atmosphere of the very, very young Earth. And here I'm talking about just a couple of million years after the formation of the solar system. So you have something that is perhaps 200 or 300 bars in pressure, and it starts to cool down by radiating heat towards space. At a certain point, as the temperature goes down and it goes below the critical point of water, then you have a phase change. What does it mean? It means that this very dense, very high pressure atmosphere is no longer able to hold all of this water in supercritical state. And so what happens? It goes from supercritical to subcritical. And this means that most of the water in the atmosphere condenses in a flash process, and you rain down global oceans on the planets.
But it happens really fast, this process?
Yeah, it would have happened in a matter of days.
That's crazy. You have from one day to another, you would have a dry surface from oceans.
Well, I don't know if I would have called it dry. You would have had a very hot surface that all of a sudden got covered by a very hot ocean. And the reason why it's very hot is that the atmosphere still had a very, very high pressure. So even with all of the water gone, the amount of CO2 was such that it would have behaved like one of these pots that you use for cooking greens at, 120 degrees. It's a pressure cooker. So you could have had the oceans have temperatures above 100 degrees because the pressure would have still meant that the water was liquid.
Yeah, I see.
Eventually, the ocean would have started to cool down. And the interesting stage, and this would have been true both for Venus and certainly for Earth, is that there would have been no emerged lands. The entire planet would have been seen from space, just water everywhere. In fact, the process that forms continental crust requires that water enter the crust and go through a very complicated process.
Okay.
The first emerged lands that you would have been volcanic arcs, a bit like the islands in Hawaii. So basically, you would have had these submarine volcanoes just growing so much that it would just break through the water surface, and that would have been the first island, so to say.
And that gives also a path for the water to come in the crust, right? Or is the water...
Indeed, because the process, there was still so much hydrothermal activity and volcanism that the crust was constantly being fractured, and the water was able to go down. Now, this is a very, very important process because it's the means by which, let's say, in these very early stages of planetary formation, the atmosphere doesn't escape to space. It escapes downwards into the mantle, because the CO2 would have been reacting with rocks to form carbonates. And these carbonate rocks would have been sequestered, subducted, that means pushed down into the mantle, and all this CO2 would have been taken away from the atmosphere. In fact, today, the Earth's atmosphere doesn't have a lot of CO2.
True, yeah.
Anyways, so why am I mentioning this? Let's move to the next slide.
Okay.
So this would have been a typical terrestrial planet. I don't know if this is exactly true for Mars, but probably yes for Venus and Earth. So water everywhere. I'm also not sure if we would have had so many clouds because they require nucleation centers to form. But let's say there would have been a lot of water. And on the next slide, we see the next step, which is with time, the water would have cooled down, a lot of the atmosphere would have been sequestered into rocks, and you would have started to form the first continental crusts. And if we go to the next slide, here we try to put everything together into one graph. So on the top part, where you see that black bar, you see the various stages in this sort of little tail of planetary formation I told you about. At the very bottom, you see the age of the solar system. And I'm not showing all of it. I show you the formation of the solar system at roughly 4.57 billion years ago. And I go up to like 3.5 billion years ago, which is the oldest traces of life that are preserved on Earth. So then if we looked in the middle, we see that there is a few, let's say, within 30 million years, we went from the magma ocean, let's say the entire surface of the planet being molten rock, to the emission of the primordial atmospheres, the supercritical atmospheres, and their condensation. You see on the top that there is a red bar. And this red bar means that probably the conditions were not ideal for the appearance of life. Why? Because the water was still too hot. You need the temperature of the oceans to go below 70 degrees for organic chemistry reactions that may take place in the liquid phase to have a bit of a chance to remain stable.
So that's why in the process of the planet cooling, then we slowly reach this threshold of 70 degrees and we slowly converge towards conditions that are suited for life, right?
Yeah, and that's what you see. I've indicated this at 4.4 billion years ago, but of course nobody's sure. But at the top, you see that for Earth, you get this blue bar. And this large blue bar indicates more or less from which time onwards we think Earth may have had conditions such that life could have appeared here.
Just a question, sorry, Jorge, from Robin. He's asking about the 70 degrees value you mentioned. What is the justification for that, or why is this threshold at this value?
It is arbitrary, I tell you, but it is taken or considered to be 70 degrees because it's the temperature at which the ribose molecule, which is a big part of RNA, is stable.
Okay.
So in other words, above that, we don't think it would have been possible for RNA to exist.
Okay, but I suppose I'm not a chemist myself. Actually, Robin in the chat is, but I suppose some chemical processes that are required for creating some organic molecules can also appear at higher temperature, and
of course,
and then create a nice environment for the life to appear in. But what you say is, for the life itself to be sustained, needs to be below.
You have to be careful. All of this is very approximative.
Mm-hmm. Okay.
I have another presentation about how and where life could have appeared, but I'm not showing it today because that would have been too long. That deals with what could have been the path from prebiotic chemistry to the first protocells and where it may have happened. Because we tend to think of life as something is dead or something is alive. But this is perhaps not necessarily true. Life has a number of functions, and a system has to be able to go from elements to a functioning system, and the acquisition of these functions may not have happened all at once. In other words, whatever assemble of molecules there was may have slowly moved towards a state of life.
Yeah, I see.
All of this is to a large extent a bit of blah blah because, first of all, nobody has been able to make life in the lab to say it was this or the other way. And it has to do a bit with thinking and what are plausible arguments. But okay, this is just to say, yes, prebiotic chemistry reactions you could have had at higher temperatures. In fact, there is a process that goes on in the crust where you have certain minerals like peridotite that is very prevalent in the mantle of the Earth, reacting with water at 200, 300 degrees to form another mineral called serpentinite. And in the process of forming serpentinite, hydrogen is degassed, which can then react with CO2 under certain chemical conditions and produce methane and formaldehyde and a whole bunch of other very simple organic molecules. So if you click once, there's another very important thing that we need to consider in this graph, and that is that as the planets were cooling down, there was still an immense heat engine that from the interior of the planet was responsible for volcanism, hydrothermal systems everywhere. And of course, the places where you had volcanic eruptions were very hot. But if you were to move 100 or 200 meters to the left or right, like it happens today for example, in the Mid-Atlantic rift, you find that you have hydrothermal systems where the fluids that come out are rich in organic molecules, and the temperatures span gradients between, let's say, 80 and 20 degrees.
Okay.
So all very nice. So, and this is considered perhaps one of the most interesting places for life to have appeared on Earth. That is in submarine low temperature hydrothermal vents, where you have the chance to use the porous matrix of the chimneys in the vent as, for those of you who like chemistry, sort of like a gas chromatograph column. It's a place where you have a continuous flow of liquid carrying organic molecules that are able to react in the pores of the mineral matrix and form bigger aggregates and perhaps become more complex. Again, it's a bit of blah blah in the sense that you try to come up with a place where you could have formed more and more complex molecules. Some people think that if you throw organic molecules at water, you are going to make chicken soup and you're going to make life all of a sudden. But it just doesn't happen because you just dilute your organic molecules in the sea.
You need to have some concentration of molecules and at some point to have chemical reactions.
You need a chemical reactor. That's what you need. You need a place where you have a constant flow of, let's say, a mobile phase, like the chemists say, so a liquid that carries stuff, and the ability to concentrate and make stuff more complex. But I'm digressing here. Let's move on with this graph. If you click once more.
Yep.
Another thing we have to think about are meteoritic impacts.
Chemicals coming from outside.
No, not in that sense. Actually, the chemicals came. Oh, there's another thing for another subject for another. If the terrestrial planets had formed only with the material they could draw where they grew, they would have been bone dry and they would have had no water and no organic molecules.
Okay.
And the reason is that inner part of the solar system is dry. And water and methane and ammonia, all these volatiles only can exist beyond what is called the snow belt. And the snow belt is somewhere around the orbit of Jupiter today. So how did we get all this water? And that was a chance happening. So Jupiter and Saturn were the first planets to form in the solar system, and they started breaking against the gas that was still in the infant solar system cloud. And like most giant planets, they would have ended inside the sun, because they start losing speed, they fall inward, and boom, they go into the star. But what happened was that at a certain point, they came into resonance, and then they were ejected out again to the place where they are now. Now, the beauty of what happened to us is that when Jupiter and Saturn migrated inwards, they carried with them planetesimals from beyond the snow belt. And these planetesimals were thrown into the inner solar system and would collide with the other planetesimals that were giving rise to the terrestrial planets. And the planetesimals from beyond, they were full of water. In fact, we tend to think of asteroids as one thing and comets as a different thing. But in reality, there is sort of a continuous of, let's say, composition. And some of the bodies in the outer solar system, they have a lot of volatiles. So They carried organic molecules, they carried ammonia, they carried methane, they carried water with them, and they went bang, bang, bang into the embryos and planetesimals that were in the drier part of the solar system and gave us everything that we have today.
But just to make it clear, this process was way before what we called the late heavy bombardment, right? It was at the formation of planets or protoplanets.
It was the formation of the planets, but the late heavy bombardment is coming under discussion lately. Some people say that perhaps there was never a big hump like I'm showing there, but it was just a continuous tailing off of the number and size of impactors.
Okay. But what does it bring, this late heavy bombardment in the system?
Well, that the possibility to sterilize and destroy. If you have an impactor that is large enough, it could totally vaporize the oceans, for example. And statistically, you cannot discount that at some point there may not have been something like that. So when you think of origin of life, you have to take that into account. Let's click on to the next slide, because now we're going to look at what happened to Mars. So, if you can go back once.
Okay.
So, the case of Mars would have been pretty similar, except that Mars is a smaller planet. A smaller planet has a number of inconveniences. For example, it cools down a lot faster.
Yeah, okay.
That's not necessarily bad, but it has a much lighter or shallower gravitational well, which means that if you have a planet whose atmosphere is relatively hot, the gravity is not enough to hold on to the particles that are in the high energy tail of the statistical distribution, and those will be lost to space. Now, initially, Mars had a magnetic field that was even stronger than ours, but we know it disappeared at a certain point. And here I'm showing sort of a transition around 3.9 billion years ago. We don't know exactly what happened, but around that time started this process of rapid loss of atmosphere and general drying out of the planet. And why am I mentioning this? Because if we look at the blue bar at the top and what we call the window of opportunity for life to appear, we see that on Mars, we have to be very careful about what is the time period that we're going to study. In other words, we have to target a landing site whose age is right. And the age is right if it is as old as possible. Now, there's another thing that is very interesting about Mars, and that is that because it's a much smaller planet, it doesn't have plate tectonics like the Earth.
Okay.
On Earth, you have the continents that are dancing around, and they every now and then they separate, they all come together, they give you Gondwana or whatever, then they separate again. We've gone through this process several tens of times. And these plate tectonics mean that at any one point or the other, most of the Earth's crust gets subducted. That means two plates collide, one goes under the other, and all of the stuff that was on the surface gets pulled down into the subsurface, where it gets cooked to like 400 degrees or something like that.
So the geological history is lost at long time scale.
So the oldest rocks that we can study are from about 3.5 billion years ago. And why have they survived? Well, they survive on something we call cratons. And cratons are like islands of material that form on the continental crust, and they stay on top. And they have been spared this process of subduction. So there's one at the tip of South Africa, there's another one in the Pilbara in Australia, there's one in northern Canada. There are maybe 5 or 6 all over the world, and they're not that big.
Interesting. What did you say the name was? I didn't hear about it before. The
Pilbara is about 1,000 kilometers north of Perth.
No, but I mean the geological name of these structures.
The cratons.
Cratons.
Yeah.
Okay. Thank you.
So what else can I tell you here? So the age is very important. But moreover, because Mars doesn't have plate tectonics, the rocks that were deposited on the surface 4.1 billion years ago, we see them. We can land there and we can go study them. So not only it's a site of that age right to go search for the traces of ancient Martian life, it may also teach us something about early Earth too, being a terrestrial planet, that we can no longer study here.
So, super cool. Yeah, okay. So but how can you...
a bit of an introduction, so to say.
How can you be so sure that the geologic activity on Mars was not involving any subduction process even in the past history of Mars? Is that because of the presence of craters on the surface?
Exactly. We can count the craters and we can tell how old the terrain is.
Okay. Okay, super interesting. A bit like the moon, actually, also.
A bit like the moon, yes.
Okay.
The only thing that is trickier is Mars has a very tenuous atmosphere. The pressure is just 6 millibars instead of like 1,013 here. But it is enough to put a dent on the very small crater impactors, or let's say the very small meteorites that would give you the smaller craters. So doing chronology of surfaces on Mars is not as straightforward as on the moon.
Okay. And good question from Ezwak in the chat. How old is the target landing site then for Exomars?
We're going to get there towards the end of the talk. If we can go to the next slide, please.
Okay.
So, there are 2 concepts I want to discuss a bit. One is this one of habitability. So what does it mean? Habitability is the ensemble of conditions that a place has or had that we consider would have made it hospitable for microorganisms. The minimum is microorganisms that would have arrived there in some way would have found conditions such that they could propagate. Now, the conditions for life to exist are much less stringent than the conditions for life to appear. That they're different things. But here we're just talking about finding traces of life. So for the time being, we're not going to make a distinction of whether we're going to a place where life may have appeared or we're going to a place where we might find fossil microorganisms. Any life is good life when you're doing a planetary mission like this. So this habitability has a lot to do with understanding the geological context. You want to go search for life in a place that you think has the highest chances for having supported life. So if you were an alien orbiting the Earth and you see what we have here, you wouldn't land in the Sahara if you wanted to look for life. You would go to the Amazon. And here we are trying to do the same. We look at what can be observed on Mars, and we try to identify conditions that would have been good for life. And typically these are sedimentary rocks that formed in the presence of prolonged low energy water. So something like in the canals of Amsterdam. We don't want the Niagara Falls. That's no good when it comes to preserving biosignatures. You want a very stable, water-rich environment where microbes could have formed, for example, microbial mats, like the Bassin d'Arcachon.
Yeah. Isn't it also the rationale for the Perseverance landing site? Jezero crater is suspected to have been a lake before, so very stable water.
Yeah, well, yeah, on the other hand, they're going to a delta, and the delta has two main components. The proximal part of the delta, the one that is close to the mouth, that is the high energy environment, where you have a river carrying deposits that encounters a lake and dumps everything. Now, that part of the delta is not exactly a very quiet place.
Yeah.
The quiet part of the delta are the distal deposits, the ones that are far away, which are typical, much finer in nature. But I mean, our perception of fluvial systems is very colored by what we know from Earth. And on Earth, deltas are full of microorganisms because there's plants everywhere. And a delta is interesting, but we shouldn't be too quick to make the connection that because deltas are rich in organics on Earth, they should necessarily be rich in organics also on another planet.
It's probably also not exactly the same science objective, because Exomars is hunting for the spots where the habitability conditions were gathered in order for the life to develop in this spot, whether Perseverance is searching for ancient traces of life. Correct me if I'm wrong, but
actually we're doing the same thing, but in very different ways. So I hope we have discussed well enough this bit of habitability. Let's move to another slide.
Sure.
The next thing we have to talk about is preservation. Now, suppose you had a microorganism living happily on Mars 4.3 billion years ago. It died. Typically what happens is when a microorganism dies, the contents of the cell are released to the environment. And what do you have? Well, you have everything that you have in the cytoplasm of a microorganism, let's say if it was a cell, plus the contents of the membrane. All of that goes into the terrain, so to say. And then you have to try to understand, how did all of that make the trip in time from 4 billion years ago to the present? For example, you may have had 1,000 meters of sediments deposited on top of the place where these microorganisms lived and died. And then that would have put pressure. Maybe there was water circulating through there. At a certain point, wind may have eroded all this overburden, all this material on top to bring back to the surface or expose the layers where the microorganisms lived. Let's go to the next slide. Preservation is very important. You need to be able to recognize what you want to study. Now, if we look at the surface of Mars, a very simple way to think about it is imagine an ocean, but it's not an ocean of water, it's an ocean of dust. And what is this dust? Well, this dust is a product of the billions of meteorites that have pummeled the surface of the planet, pulverizing it, plus the result of wind erosion. But within this hopeless sea of dust, we have these outcrops, these bits of indigenous rock that break through the surface, a bit like the tip of an iceberg, that we can study. And so this is super important for us because if you choose your landing site right, you would select something that has outcrops that you can approach that have the right mineral composition. And what is the right mineral composition? It's what you would have had in a water-rich environment of the type I mentioned before. But if you click once, we will discuss now what happens to the material close to the surface. First of all, you have UV light, because Mars doesn't have much oxygen, in fact has almost no oxygen. There is no ozone, or that's not true. There is some ozone, but it's very little. And so the UV dose that reaches the surface is much higher than it is on the surface of the Earth. So basically, we quickly inactivate anything that is alive on the surface or cream any sort of organic compound that is lying exposed on the surface. The next thing we need to worry about, if you can click again, please, are oxidants. What are oxidants? For example, the famous perchlorates that Phoenix, Viking, and Curiosity detected. There can be others, but these are oxides, oxidants, like, I don't know, hydrogen dioxide or the perchlorates, other oxychlorates. Normally they don't do anything. They're just sitting there, but under the right humidity conditions or under the right temperature conditions, they can dissociate, creating radicals, for example, oxygen, that then go around and scavenge organic molecules, oxidize them, and basically degrade them. And then we have the final destructive agent, which is ionizing radiation. The Martian atmosphere is so tenuous that the cosmic radiation that comes from the center of the galaxy penetrates through the atmosphere and even penetrates into the subsoil. And so if you want to have a fighting hope of being able to study chemical biosignatures that may have been deposited in the geological record 4 billion years ago, you need to be able to, if you can click again, please, go beyond all this bad juju that you have close to the surface. And this is, if you like, the mantra of the Exomars rover mission.
Okay.
Rosalind Franklin carries this drill to go beyond this destruction horizon.
Can I just summarize if I understood correctly? You said at the beginning that Mars has had a strong magnetic field, right? Maybe even larger than the one on Earth today. But since you highlighted the fact that today it has no longer a magnetic field, you determined a time period during which the magnetic field might have faded. And then from the period of this magnetic field fading towards today, you computed the cosmic radiation dose that could have impacted the potential subsurface or surfacic life microorganism. And you said, okay, it had completely discarded the possibility of finding anything below 1.5 meters, but we might have a chance below that, right?
Yeah.
Above, sorry, sorry.
Okay, let's make a few remarks here. First of all, the magnetic field disappearance is interesting, but doesn't necessarily mean that it was the cause of the drying out of the planet. It's just curious that it happens more or less at the same time. It is also more or less the same time when the giant volcanoes of Mars formed. You have the Tharsis bulge, which is like a very hot spot that created Olympus Mons and some of the other planets, volcanoes.
Mm-hmm.
And so it all happened more or less around there, but it's very difficult. I hesitate very much to say that because the magnetic field disappeared, the atmosphere went away, because actually planets that have a magnetic field lose atmosphere faster than planets that don't. On Earth, we lose a heck of a lot of atmosphere through the auroral ovals, precisely because we have a magnetic field that
interesting.
A magnetic mirror and creates jets of atmosphere that extend in both poles directions, and we lose into space.
Oh, okay. This is counterintuitive in my mind, but okay, very, very interesting.
No,
but I didn't understand this concept before. Okay.
No, but I like to stress this because this is a very important thing, and I thank you for this, this question. So what about, how do you explain the fact that Titan has an atmosphere of 2 bars?
That's true.
Slightly larger than the moon, no magnetic field, and Venus has an atmosphere of gazillion, I don't know how many bars, by like, I don't know, 100 bars, and has no magnetic field.
Yeah, okay. Well, the pieces come together. Okay.
I'll give you the answer. The answer is in the interplay between the temperature of the atmosphere and the gravity of the planet. You can have no magnetic field and a hot planet, but if it is big enough, it will hold to its atmosphere, which is the case of Venus.
Mm-hmm.
Or you can have a very tiny planet like Titan, well, it's not that tiny, it's pretty large, but with a very dense atmosphere. And why is it able to hold to it? Because its temperature is minus 160 degrees.
Mm-hmm.
So that's a trick. It's not having or not having a magnetic field.
Yeah, okay.
Gravity and temperature.
Okay, perfectly understood. Very nice.
Okay. Anyways, so what distinguishes Exomars from any other mission is the fact that we carry with us this drill able to penetrate 2 meters into the subsurface. But this may not be enough, because 4 billion years is a long time, and sure, we know more or less what the radiation dose reaching the surface of Mars is today, but you have to think of the radiation as sort of it's a machine gun shooting bullets, right? And these bullets are, the target is the organic biosignature you want to study. And so this machine gun is actually cutting or shooting at the functional groups in your molecule and cutting them off, degrading it to the point where eventually you cannot tell what the mother molecule was anymore.
Yeah.
But Mars is not a static planet. There have been deposits that were laid over and then were eroded. So it's not only important that you're able to excavate below this organic destruction horizon, but it's also important that you try to understand you may have had additional benefit from some material that may have been deposited on top that was later eroded.
Okay.
So let's move on.
Okay.
So we come a bit to what it is that Exomars carries in terms of payload. We have several instruments that are very innovative and very performant, and some that are less so. You have to think that we started working on Exomars around the year 2002, and when it was first approved in 2005, but they didn't quite give us all the money we needed, we were thinking of launching around 2013. So gathering the money, the various problems we have had, blah, 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 have postponed this launch. And the result is that a few of our elements are not as up to date as they could have been if we had started designing the mission, let's say 6 or 7 years ago. Nevertheless, some things are important. So for example, we have a set of wide-angle cameras. They see like the human eye sees, so it's a field of view of roughly 50 degrees. And these we use for taking stereo panoramas. And then we have the high-resolution camera that there is shown HRC. This is a bit like a teleobjective on a camera. It corresponds to like a 300 millimeter teleobjective. And co-registered with that high-resolution camera, this Iceland below is an infrared spectrometer. So how do we use this ensemble? So we take a panorama with the wide-angle cameras, we send that back to Earth, and then we concentrate then the high-resolution camera on targets that could be interesting. And the infrared spectrometer tells us something about the mineralogy, because on Mars everything is brown, and one rock looks like the next from afar. So being able to have this bit of information about mineralogy is important. And that is the sort of information that we use to decide where to drive to. That plus all the orbital imagery we have. But to drill down to 2 meters takes us about 5 or 6 days.
Really? Oh, wow.
Yeah. So it is a very important commitment from the point of view of mission operations. So what does that mean? It means that we need to have some information that tells us that if we start drilling here, we're not going to find a big fat basaltic boulder that's going to stop the drill. And we want to know also, if we're looking for a sedimentary deposit, how far we should drill down. So to help us with this, we carry 2 instruments. We have the ground penetrating radar Wisdom, which by the way is a French instrument.
Okay.
That has a resolution, a depth penetration of roughly 3 meters, and gives us a stratigraphy with resolution of 2 centimeters more or less. And we also have a Russian neutron detector that tells us how much water we have. Believe it or not, in this mission, we don't want water. And at a certain point, I will explain why. A bit of water is okay, but too much water makes our life miserable.
Okay.
Let's move on to the next slide, please. So let's assume we approach an outcrop. The first thing we can look for are physical biosignatures. This is something that also Perseverance will try to do. Actually, it's more or less all that they will try to look for, because the chance that they will find organic molecules in a good state of preservation at the depth they can get to, which is roughly 6 centimeters, are not super high. They will find organic molecules because also Curiosity found them, but most likely these are meteoritic delivered organics.
Okay, yeah.
So coming back, let's assume that we approach an outcrop. Well, it's very important that we be able to study it in detail. You can look for laminations, the size and shape of the grains, tell you something about how the mineral grains were transported, about the origin and history of the rock, etc., etc. So for that, we have this close-up imager that is called Clupy. That's Swiss. Let's go to the next slide, please.
The drill.
The drill. The drill it's like a Swiss watch. It's a very complicated piece of machinery, but it's a wonder to behold. It's very nice. It's like a mini oil platform. It has one drill. Actually, we have two drill bits because we have one spare, but let's say the main drill bit, which is what you see on the far right at the top, that's the drilling element. And then you have 3 extension rods. And on the drill tip, very close to the tip, we have a miniaturized infrared spectrometer that shines infrared light through a sapphire window on the side, and therefore we're able to study the mineralogy as we go through the drilling process.
That's crazy. So the spectrometer is only located inside the tip?
No, not quite. It's just the lamp, and actually we have optical fibers with special connectors running through the entire drill string. And so we carry the light upwards. The spectrometer is sitting at the top.
That's crazy. Because if you keep adding some more tubes, but you have inside you still have the fibers, how do you manage that?
Well, at each, okay, let's assume two fibers come like this. It's super difficult to keep them aligned, and also as we drill, the entire drill makes some oscillatory motions. So how do you get the laser light? Sorry, not the laser light, the infrared light aligned between the fibers? Well, we have a telescope, miniaturized telescope systems that actually expand the light beam for the connection and then concentrate it again. So we have that at each junction.
Wow, okay.
So, and of course, the more elements you add, the poorer your signal to noise ratio. So when we have all 4 strings, we are getting about 25% of the light that we would when we're using just the drill bit.
A question that Isabel wanted to ask is, have you taken into account the issue that was encountered during the InSight mission on the instrument, the mole, the HP3 mole, that was, it was not exactly a drill, it was more like a hammer system, but did you take into account the outcomes of this experience?
Actually, that system, that instrument was an Exomars instrument. A long time ago, when the entire landing system was being done in Europe, we were going to instrument the lander, and actually all the instruments in InSight are Exomars instruments.
Even the seismometer?
The seismometer was proposed for Exomars, and the mole was proposed for Exomars. We started the development of those instruments under Exomars, but then when we moved first to the cooperation with NASA and then with the Russians, and we abandoned the instruments on the lander, these payloads looked for accommodation elsewhere, and they ended up in InSight. So we know the mole system. In fact, we tested it. At a certain point, we were not sure whether we should have the mole or the drill. And I remember in 2004, we went up to the Etna in Sicily, and we took the drill and the mole with us and did some tests. And immediately we realized, forget about the mole. The mole has has the advantage that it's a relatively simple system, but it needs to be very well supported to do the penetration. Because in essence, what you want, the mole has a body in two parts. The front part hammers, pam, pam, pam. But the penetration relies on the fact that the friction against the aft part has to be higher than the force that the hammering perceives as obstacle. So what we found was that any time that the mole was not well supported on the back, or that it encountered, it could be anything. It could be a rock. It could be a horizon where the material would suddenly go from being soft to being slightly harder, and the mole would start to deviate. And once it started turning, it didn't take very long to run into trouble. Now, I'm not sure what exactly happened on InSight, but we came to the conclusion that it was risky, and that if we wanted to be able to get 20 samples or so, the mole was not the right thing for our rover.
So instead, a 2-meter drill.
Yeah, and believe me, many times over the course of the mission design, they tried to cut the penetration, and we had to fight like tigers to maintain the 2 meters.
That is crazy. So, yeah, so this system, just to summarize, you have, of course, it is not a plain 2-meter drill, so it's cut in four parts. And then, so there is a system that grabs the first part, starts drilling with it, and then what happens? Does the first part stays into the ground, and we grab the second one?
That's right. So a mandrel is in charge of doing the drilling, and he goes down through a helicoidal shaft. When he gets to the bottom, there is a carousel that with a robotic mechanism that picks up the next bit, puts it on top of the bit that's on the ground, screws it in, and then the mandrel travels up, grabs the piece at the top, and starts drilling again.
But that means you have the axis of drilling needs to be really, really vertical, otherwise you might not be able to plug the next drill part, right, on top. Is that an issue?
Yeah, there is a maximum angle that we can drill at, and is not very high if you want to be able to attach pieces.
Okay.
I think it's 5 degrees or something like that.
Interesting.
So yeah, basically you drill vertically down. I mean, you could drill at an angle if you only use one drill rod.
Yeah, I see. But okay.
We should move on, because otherwise...
Sure.
I'm happy to talk for hours, but...
No, you're right. I keep an eye on the time as well.
In this little movie, you're going to see sort of a depiction of a rover. You see the Vivaldi antennas of the ground penetrating radar on the back. Then you see the drill moving from the drilling position to the sample delivery position. You see that little hand that comes out at the front that receives the sample?
Yeah.
And okay, here the drill goes back to the drilling position. We can move on.
So that means you have 5 to 6 days to retrieve the samples and or to drill down, or 5 to 6 days in total to also deliver the sample?
No. We assume a penetration of roughly 50 centimeters per day. So, but this depends a lot on what sort of terrain you find.
Of course, yeah.
So it's sort of a bit of an average like this. So depending on how tough the terrain is and how deep we want to go, it could take from, I don't know, a few hours if you just want to drill something in the surface. down to perhaps 5 days if you're going to 2 meters. So what you see here, this is not the flight model. This is actually the ground test model, which is a carbon copy of a flight article that we have at the Rover Operations Control Center, the ROC, like we call it. And we use this for testing sequences and for debugging. So it has basically everything is copied in this thing as it is on the flight model. There are a few differences. For example, here you see that the drill here is open. You can see what's inside. So this was no, I mean the image on the left. You see that the front cover of it, no, on the side of the drill.
Okay, this panel.
On the actual flight unit, all of that is enclosed, so we don't get so much dust inside. And in the middle, you see the drill delivering a sample, and you see these brushes, these metal brushes. When the drill bit is retracted inside, they take the dust off the auger. The auger is this helicoidal blade that is the most important part of the drill. Is the one that takes the fines out of the hole. If you can't transport the powder out of the hole, you're not drilling.
Yeah.
And you see that the drill has actually a sample chamber. So the way we drill, when we drill, that hole that you see at the front is actually plugged. The tip is pushed all the way forward. But then when we get to the place where we want to collect the sample, the drill keeps on turning and the piston in the center starts to retract. So basically the sample builds in the chamber of the drill. Like the periphery of the drill keeps on penetrating, but the center part just grows into the drill.
But how long will the sample will be in the
3 centimeters, like a piece of chalk.
Okay.
And then we have a guillotine at the center that can cut it off and close the front.
How can you ensure that you are not contaminating the next sample with a bit of samples of the previous sample?
We are.
Okay.
For sure. What we have are requirements for what is the maximum amount of sample N that we want to see with sample N plus 1. And over the entire sample processing system is about 5%.
And okay, but on a unique location, I guess it's acceptable. But if you move and drill on another location, that might be a problem, right? If you want to make science out of.
Well, there are things we can do. We have blanks, so that's fused silica neutral material. We have 6 of those that we can pop in. Although reality, we prefer to use them for calibration. But the other thing you can do is you can dip the drill tip into regolith at the new place you're going. You collect and eject material a few times, and after that, your drill is full of the new place.
Okay, nice.
Can we move on?
Yeah, sure.
Okay. Here I tried to show you what happens inside the analytical laboratory. This is sort of the heart of the rover. And if you can click.
Yep.
So there is a carousel. You're going to see the sample coming there. And after we drill the sample, the first thing we do is we crush it. Why do we crush it? Now, the guys doing mineralogy would prefer that we don't. But the people who are looking for chemical biosignatures, they want to see the particles as small as possible to maximize the surface of material that can be interrogated. So for mineralogy, the bigger the particles, the better. For chemical search, the smaller the better.
Okay.
So we try to strike a happy medium with a rock crusher, and we modulate the gap between the jaws as we crash. So we get material between 1 and 500 microns with a peak in the distribution at 300 microns. And that's about right. So this powder is first put onto something called a refillable container. Looks like a little bathtub. We'll see pictures later. And there, the first instrument to look at it is another French instrument. It's called Micro Omega. And Micro Omega it's a wonderful instrument. If you can click once more. Okay. You know, when you take a picture with your digital camera, you get an image that is red, green, and blue, right?
Yeah.
So with Micro Omega, we can get a picture that is red, green, blue, plus 320 infrared spectral steps. So in essence, it's a visual plus infrared imaging spectrometer, which means that every pixel in the image has mineralogical information besides just the picture. And then we have a program in the rover. This is the first bit of artificial intelligence we have on board that analyzes for every pixel the infrared absorption bands, classifies the mineral grains in terms of their mineral composition, and then is able to pass the coordinates for the mineral grains of greater interest to the rover computer, which then moves the sample tray under the instruments that have point and shoot lasers. If you can click once again. So that's the classification of minerals. For example, we see a few here. And then if you can click again, then we see what the resolution is. For Micro Omega, each pixel is 20 microns. Then the Raman spectrometer, which is a laser that shoots and obtains Raman spectral information, has a footprint of 50 microns. And so we can put the right mineral under it. And then MoMA, which is the largest instrument in the payload, is bigger than all the other instruments combined, and is by far the most expensive instrument that we have ever worked on. Is more than 120 million euros. That is the one that does the analysis of organic molecules. And for the first time, we have this laser desorption capability, which allows us to extract organic molecules without decomposing the perchlorates, which means that we do not suffer from all the problems that Curiosity has had with SAM. Besides being able to use laser desorption mass spectrometry for the analysis of organic molecules, if you can click again, we have a carousel with 30 ovens in which we can do the more typical type of analysis that Viking did or Curiosity has done with SAM, using the pyrolysis, so heat plus derivatization agents for gas chromatography and mass spectrometry.
But all the analysis before MoMA are non-destructive, right, on the sample?
Yes, including MoMA laser desorption. That is also non-destructive. But the stuff that is shown in the carousel, that's done on the refillable container, whereas for the GCMS part of MoMA, we need to use the ovens. If you will see this in the next slide, please.
Yeah, okay.
So, this is a pitch. If you want to learn more about the mission and the instruments, there was a special issue of astrobiology that came out in 2017 that is open access. Anybody, cool. If you type Exomars astrobiology, it will take you to this collection. It's 10 papers. One is for the mission and one for each one of the instruments.
Very cool. Some nice reading for the night.
It's guaranteed to put you to sleep. It's pretty dense stuff. So here I want to show you all the pains that we have gone through to try to make sure the ultra clean zone, which is the part of the analytical laboratory that comes into contact with the sample, is indeed ultra clean. So the usual part of the spacecraft is done under ISO 7 conditions, which are the clean conditions that you have for example, the ones that were used for assembling Perseverance and Curiosity. Mm-hmm. But the parts of the analytical laboratory that deal with the sample go into that glove box train that you see on the back. And this is ISO 3, which is the level of cleanliness that people use when working with things like Ebola virus and chemical weapons. So it's super high cleanliness. And in fact, there are 4 stages, and it takes about a week for something to be able to go from the entrance to the last assembly stage. And every single nut, bolt, washer, whatever it was used, and all the tools had to be dry heat and plasma, hydrogen peroxide plasma sterilized, go into that chamber, every one of them labeled and in its own container, so that people could assemble the analytical laboratory from the outside without actually having to touch anything. And once it was finished, it was overpressurized 100 millibars above ambient pressure, and only then taken out and integrated with the rest of the analytical laboratory.
That is crazy. Just before going to the next, I wanted to show the first drawing that Loiseau made. Here we go. I don't know if you see it, Jorge. I'm showing it on the screen right now.
No, I don't see it. I saw a black thing.
I'll send it to you after, but basically you have
I could try to see if I see it on one of the other windows.
It's basically the Earth, I guess it's the Earth and Mars that are actually doing an interview just in front of the amino acids, and the amino acids say, well, we have some certain standards in terms of habitability. So it's like you go, you don't. That's really a cool drawing. I can actually maybe show you on Skype, but no. I mean, it's too complicated for me to change that right now.
Maybe you can send it to me later. I'd like to see it.
Yeah.
It's interesting that amino acids, they also exist.
I sent it to you to the chat.
Material. Oh yeah, I see it now. That they exist also in cosmic organics. You can find them in meteorites, but they have some interesting properties, like the ability of being chiral, that can be diagnostic of biology. Unfortunately, amino acids they're very cool as biosignatures, but they're also very fragile.
But very cool drawing. Thank you so much, Loiseau. Thank you so much.
Who sent it?
Loiseau in the chat, who stands for the bird.
Nice. Very cool.
So yeah, coming back to the cleanliness of Exomars, you were highlighting the process for the clean ISO 3 environment, which is crazy clean.
Yeah. It took almost a year to assemble the inside part of the analytical laboratory and test it.
Isn't it the mission for which the cleanliness is the highest ever?
No, I wouldn't say that, because the parts of Perseverance that deal with the sample are as clean as these ones.
Okay.
The thing is, so I would expect that the caching system, everything that comes into contact with the sample, would have been built to the same level. the rest of the rover that doesn't touch the samples would have been ISO 7.
I see. Okay.
It's the same for us. This is what it's called in planetary protection category 4B, which is when you, so Spirit and Opportunity were category 4A. That's a mission that goes to Mars to a non-special region, which is a region where we don't think Earth microorganisms might propagate, and doesn't look for life. So looks for rocks, water, whatever, but not life. So that's category 4A. Category 4B is a mission that goes to a non-special region but does look for life. And that's Exomars and to some extent Perseverance, because Perseverance is the first element of a category 5 mission, which is Mars sample return. And the highest category for robotic missions that land on Mars is category 4C, which is a mission that goes to a special region where we have reason to think there is either life or that Earth life could propagate. And there has been 2 missions, 2 landers that were category 4C, and they were the Viking landers. And in that case, you have to heat sterilize the entire spacecraft.
Wow.
And they had a humongous oven in Cape Kennedy where they stuck the entire capsule for Viking and cooked it at more than 100 degrees for a number of days.
Wow.
And the reason was that in 1976, they thought that Mars was going to be full of microbes. So they had to prepare for it. And they did. And none of our spacecraft would be able to survive that sort of treatment today.
Crazy. But when you heat up this probe, but then you integrate it on the launcher, and you launch it passing through the atmosphere and everything, it completely loses the I mean, it gets contaminated at some point, right?
You mean the outside, for example?
Yeah, the outside.
Yeah, but you probably don't care too much, because at the moment you go through re-entry on Mars, that the whole stuff is going to be cooked to several thousand degrees.
Yeah, okay. Okay, that makes sense. Okay, coming back to Exomars, I'm skipping one slide. Okay.
So that's the Analytical Laboratory drawers ultra clean zone. You don't see the rock crusher here, but you see the 2 dosing stations, which are those sort of cones at the top. And then you see the carousel with the ovens. And the refillable container, it's not easy to see. But this is the bottom part of the Analytical Laboratory drawer. You can go to the next slide.
Just a question. You have a limited amount of samples. That means, are you able to drop some samples if you don't want them anymore?
Well, that's an interesting question. We actually drop every sample. After we are done doing the analysis, we don't want to keep the material in the dosing stations for too long, because there is always the risk that it might cement. If, for example, it has residual water, I mentioned that we didn't want to have too much water.
Yeah, you did, right.
So let's say we have more than 5%. That humidity will interact with the mineral grains and may lead to cementation. And so to deal with that, most of the mechanisms have ultrasonic vibrators, piezo vibrators.
Really?
So you can shake everything. The rock crusher even has a hammer that is able to deal massive blows to make sure stuff doesn't attach or stick too much. This machine is very, very complicated.
What a crazy piece of engineering. It's wow. Okay, but why so many sample devices then? If you
you need to be able to, you crush the sample. Let's say you drop the sample in one of those cones, the dosers. Then you have the dosing stations at the bottom have rotating spheres with imagine a sphere like this, and there is a missing piece. So that rotates, and every time it rotates, it picks up a bit of sample and drops it below. So when you go to the refillable container and you move over the bathtub, you have to drop, move, drop, move, drop, move, drop, move, and then you have to have a blade that flattens the sample. And you want no more than 100 microns between peaks and valleys in sample space, so that when you move below, for example, micromega, the surface of the minerals are in focus.
Yeah, I see.
And then we also have another blade that actually cleans the refillable containers so we can use it again. Wow. There's many robotic mechanisms in this thing.
It's awesome. It's crazy.
Yeah, we're pretty happy. It's so that's what it looks with the instruments integrated. So now you see what you saw before is just the gray part at the very bottom. And on top of that, you have all the instruments, MoMA, the electronics, micromega, RLS. So it's very complicated. And on top of that, it's all pressurized. And you have a pressure release valve, because when we launch and go into space, you need to be able to vent.
You mean pressurized all the, inside
the ultra clean zone. All of that is kept at positive pressure to avoid that Earth's atmosphere can get inside.
Oh, that like a clean room. It's crazy.
Yeah. Even so, we still get stuff inside. So we're constantly monitoring and the ultra clean zone is so clean. Assume that its volume, it's the size of planet Earth. So the maximum amount of contamination that we allow inside is the size of a football.
Oh my God. Okay.
And still we get whiffs of bits of glue and other stuff, and MoMA can see it. So yeah, we're putting a lot of attention in making sure that thing is as clean as can be.
Crazy.
Let's go on.
Yeah, sure.
You tell me if we're going too slowly, because
no, it's fine.
falling asleep.
We only have some pictures left. It's fine. We can just continue describing the pictures.
Yeah. So this shows you the bathtub. That's what we call the body of the rover. So these guys are pointing to what you see the first. Yeah, the first 2/3 of that is the Analytical Laboratory seen from the top, and the back is the service module, where has further back.
Oh, this one?
No, that's the front, the other back.
Ah, okay, this one? Ah, no, you mean this? Sorry.
No, the stuff with
okay, the full of cable stuff.
Yeah.
Okay.
So that's the part that has the transmitters, the batteries, the radioactive heating units, all of these other, let's say, service components. Can we go to the next?
Sure.
So here you see this taken in Airbus in the UK when the guys were assembling the rover. This is the moment they attached the mast, and they were trying to see if PanCam could see something. You see the antennas for the radar at the back, and the wheels are missing.
Yeah. It's crazy the amount of cables. I'm always amazed.
Yeah, it looks much cleaner in the simulations.
Yeah.
Can we go to the next?
Yeah, sure.
So this is a flight model. On the left, you see it. This is in Cannes doing thermal testing, and okay, there are some protections in the front of the rover, but this is a flight rover with now the wheels are on, everything is in as it should be, and on the right instead you have the rover suspended, because here we were calibrating the ground penetrating radar. So we elevated it a couple of meters above a bunch of metallic targets, and we exercised the instrument.
Okay.
We can go to the next slide, please. So this was taken in Cannes about 2.5 weeks ago, when the rover arrived from Torino. You see the lander on the left. That's also the flight lander. And the carrier module on the right, where it says OHB. And so this is like the whole spacecraft is like a Matryoshka doll, and at different points we have to take bits and bobs in and out to perform the different tests. You see all these cables coming from the outside of the bathtub and going to the electronics. That's because, on the side, that's because the actuators for the motors on the rover are actually outside the warm body. So for the first time, a mission to Mars is flying what we call cold electronics. They have to take minus 120 every night.
Yeah, so far the motors are inside and they provide a torque, right?
No, in this rover the motors are outside, and also in the American rovers the motors are outside.
Okay.
But we'll talk about the locomotion system a bit later.
Okay, because I have some further questions on the wheels and okay.
Yeah, let's move on.
We see them.
That's another. You see the rover here again. You see the rear jacket. That's a flight article on the back. And here what they're doing is they're attaching the rover to the pallet. This pallet is gets then bolted onto the lander, but it is through the pallet that the rover communicates with the lander and receives energy.
Okay, it's basically the interface during the flight.
Yeah.
Okay.
And also after landing, at a certain point we pop the umbilicals off, fire a bunch of pyros, and then the rover is free. Next slide, please. So here's another view, perhaps in more detail. You see the wheels are very complex because there's a very complicated set of internal springs in titanium and steel because the wheels are flexible. We do that because the wheels are relatively small and the pressure patch on the ground is tiny. But by having flexible wheels, we behave a bit like when you want to drive your pickup in the desert and you take the air out of the tires to increase the contact patch. So with flexible wheels, we get a contact patch that is 30% higher or larger than what we would have with, so the wheels are 28 centimeters in diameter, but they have a contact area as if they were 40 centimeters in diameter.
Okay, I see. And these pictures are crazy, by the way. When was taken this one? Do you know?
It was taken the same day that it's about 2.5 weeks ago. 2.5
weeks, very recent. The rover right now is in Torino, right?
No, everything is in Cannes.
Cannes? Okay.
We finished the mass property, so moments of inertia and center of gravity plus mass balancing for the lander, then for the lander inside the capsule, and then for the capsule connected with the carrier module, so the entire spacecraft composite last week. And now we are starting electromagnetic susceptibility tests.
Nice.
To see how the various boxes may interfere with other components.
Cool.
Next slide, please.
Yeah. So cool.
So here you see the rover flight model on the pallet integrated on the lander.
And all the cables and everything we see here is in flight configuration?
No. Like you see all those white cables there in the front?
I was about to ask.
Thermocouples.
Okay.
There's a lot of junk here that is still attached there for the purposes of testing.
And we have the next drawing from L'Oiseau. I just let you comment on this slide, and I'll download it in the meantime.
So this is to talk a bit about the locomotion formula for the rover, because it's really advanced compared to what the US is flying. So let's say I told you in the beginning that a bunch of things that we have are a bit old compared to what Perseverance has, but a few things are still super state of the art. And the locomotion system and the drill are two of them, the Analytical Laboratory as well. But what do we do that is different? And that is, in the US missions, they only steer the end wheels, which means the wheels in the middle cannot rotate. I mean, they rotate in the sense of being able to move forwards and backwards, but they cannot steer like this. Whereas we steer all 6 wheels, and that is very cool because it allows you, for example, to crab. And this means you can rotate all 6 wheels in a direction, and say you want to image an outcrop. With the US rovers, you have to go back and move to a new place, and forwards and back and forwards. We just move sideways all 6 wheels, and we just pan. We move sideways like that.
Yeah, like a crab.
Very useful. Like a crab, yeah. And the other thing is to erect the rover, to raise it, we had to include knee motors. And these knee motors, which I guess you see them on the drawing on the right, exactly where you put not there on those we can use for wheel walking. That means that you have to think of this rover a bit like a supermarket trolley, right? It drives great in the parking lot, but if you take it to the beach, it's not so great. And why is that? It's because the wheels are relatively small, and so the pressure on the ground compared to, let's say, Curiosity or Perseverance is higher. So there is a higher chance that you may start to slip or eventually get stuck. So how do we deal with that? Well, if we detect excessive slippage, then we can go into what we call the wheel walking mode, in which the wheels are used as feet.
That is crazy. And we have a video.
I included a video.
Yeah. Guys, if you haven't seen that, you might want to come back to the screen, because this is crazy. It's never seen. It's a never seen technology.
So this is a facility we have in Switzerland for testing egress and locomotion. It's basically there's a bunch of platforms that we can use, but this is the largest. You can fill it with representative material, and you can incline it to various slopes. So if we go to the next slide, you will see some videos of the rover. These are accelerated. Oh, it's strange. The one on the right.
I don't know why. But we see this one properly.
Yeah, I don't know why the other one went
I don't know.
sideways. Anyways, you see this is what we do is we can use it in many ways. This is the one we found works the best. But we can skate, or we can advance one wheel at a time. And here we are negotiating a slope of flower-like, so very, very fine sandy terrain at a slope of 21 degrees, which is very, very steep.
But does it mean you give yourself the possibility to explore such areas, or is it more a system that is good to have if we by any non-chance get stuck into.
Exactly. That's the way to look at it. We felt that we needed to have a safeguard to avoid getting stuck like Spirit got stuck at the end of its mission. Admittedly, by then it had one wheel that wasn't working anymore. But we want not to have to deal with that situation. The only thing I have to say, though, is that, of course, we use more energy, and we are a lot slower when we are wheel walking.
Yeah, I can understand.
So it's an emergency type of situation.
But it gives so much flexibility in the navigation system, it's crazy. You can do pretty much anything.
Well...
Climb mountains, swim into rivers and everything.
Let's say it's nice to know that you have this possibility. I'm not sure that we would look for places that are complicated enough that we would need to use it often.
Yeah. Just before going to the next slide, I wanted to show you the next drawing. Let me just... Here it goes. It's about contamination, and let me just send it to you through Skype. Can I do? No, that's not it.
Something is coming.
Here we go.
Oh, there we go. Oh, yes.
I mean, yeah, you were not such impacted by COVID restriction. That is crazy.
We've had a lot of problems with COVID.
No, okay, I mean, I imagine. But in terms of contamination itself or working with a mask, no.
Not in terms of contamination, but we are a very international team. I mean, the rover was assembled, the spacecraft was assembled in Turin, in Italy, the rover in the UK, the locomotion system comes from Canada, the computer from Sweden, the lander is made in Russia with a whole bunch of components from Europe. We have seas of engineers that need to travel from one country to another. So this COVID thing has been very complicated.
Yeah, I can imagine. Let's move on. Launch.
So, yeah, let's click again. So this tells you a bit about when we're going, when we're landing. So we will land at around 4 something in the afternoon on the 10th of June, 2023. And if we go again.
Yeah.
Here I show you some pictures more of the landing stage. So that was during assembly in Torino.
Cables again, cables. I'm so impressed. Do you know how much the cables weight in terms of percentage of the total mass?
No, I don't know. But typically, we have on all these spacecraft we have several hundred kilos of cables.
Yeah, it's crazy. Wow. So this landing module is made in Russia, right?
Yeah, even though we provide a lot of stuff for it. The radar is European, the computer is European, the software is European, the antenna for communication, or some of them are European. The parachutes are European, the ejection system for the parachutes is European.
Okay.
It's perhaps the most challenging part of the mission because the components are, the interfaces are not that clear. The Russian units use, for example, Russian connectors, which look nothing like European connectors.
So a lot of challenges into the interfacing. That was one of the questions I wanted to ask is how difficult was it to manage a project which is in such a close cooperation with Russians and a different agency in general?
It's difficult because they work in a different manner than we do. We are very paper heavy. We write a lot of documentation and we simulate a lot, and at the end we test. They use a different approach. They build a prototype, they test it, they learn from it, they modify the prototype, they test again, they learn. So then they come to you with a very thin document that reports the results of how it works and the final test. But in the middle, they've tested like crazy compared to us, and of course in the end, it all has to work together, and we all have to be convinced that we've all done our bit and that it's going to work. So, okay, we've been working together since 2013 now. So I'd say that we have had to learn from each other. And okay, as you can imagine by now, we have found a modus operandi or a working method that functions.
Yeah.
So, but it has been interesting.
Very interesting. I see a questions in the chat about the descent, but we'll come to it in a few minutes.
So here this is the lander is. This was about 10 days ago. It's when we were putting the rear jacket on the lander with the rover inside before going to do the mass properties test. Next slide, please. And here is the spacecraft, the entire spacecraft component. And one way to tell whether it is a flight model is the mylar on top of the heat shield is silver for the flight unit and gold for the test unit. We actually have two heat shields. One in which with apertures through which we can lower gases and electricity to, for example, the Analytical Laboratory drawer and other parts of the rover, and the flight unit, which of course it's one element. So this is everything as it will be launched to go to Mars.
Cool.
And as you can see here, there are not many cables.
Yeah, now it's all tidied up. The parachute. This is a hot topic.
So we are getting to the end, but I wanted to talk a bit about this because it's complicated. And why is it so complicated? We would have preferred just to have one supersonic parachute, like the American missions do. But when we were sizing the lander, and the Lavochkin is in charge of the descent engines, and the descent engines are a new development that was made for Exomars. These are throttable engines that don't exist in Europe. So the Americans have the Aerojet engines that they use for MSL, and these are big beasts that they develop for other things. For example, we use them also on ATV, but not throttled. But here for landing, we are using these Russian engines, and they work in a different way from the American engines. And so when we were requested to meet the Russian requirements for which speed we should be moving at what altitude, we found out that with a supersonic parachute alone, we couldn't make it. And so we had to build this monster of a subsonic parachute, which is of the same design as what the Apollo capsules used or the Soyuz capsule used. It's
crazy.
It's called a ring slot parachute. The supersonic one is called a disc gap band, which is also what the American missions use. And typically you would eject the parachute into the slipstream using a mortar. But there are so many, the parachutes are so big that if we had to use such big mortars to eject these parachutes, there wouldn't be any room for the rover. So rather than having these huge mortars, what we use are pilot chutes. So there is a little mortar that ejects a pilot chute, and then the pilot chute extracts each one of the parachutes. Mm-hmm. In reality, it doesn't extract the parachute. What it extracts is the bag, the extraction bag. The parachute is attached to the capsule, and it's the bag that flies away from the parachute.
It's basically like a parachute on Earth when you go skydiving. It's the same. You have a bag and you have an extractor, which you don't have a mortar, so you manually extract the extractor, and with the drag, it pulls the big parachute from the bag.
Right. So it's the same here. And so to talk about the descent, we arrive at Mars at roughly 20,000 kilometers an hour. Mm-hmm. The whole descent takes about 6 minutes. So the first 3 minutes are sonic phase, where we go from 20,000 kilometers to roughly a bit less than 2,000 kilometers an hour. And we pop open the supersonic chute, and we hang on the supersonic parachute for just 20 seconds. And that decelerates us from roughly, let's say, 1,700 kilometers an hour to about 350 kilometers an hour.
Okay.
Then we open the subsonic parachute, and we hang on the subsonic parachute for a long time. And we go, the terminal speed with a subsonic parachute is some 150 kilometers an hour. And this happens at roughly, we let go roughly 1,000 meters above ground. And we execute a diversion maneuver. So we fire the engines and move to the side some 300-400 meters to avoid that the parachute lands on us. And by then we're going still at 150 kilometers an hour, but we are 500 meters from the ground. And then we become vertical again, and we fire the engines like crazy for 7 seconds, and we touch down at less than 10 kilometers an hour.
Okay, so just a reminder for the audience: there is no sky crane. It's like a platform landing with the feet on the ground, right?
Mm-hmm.
Okay. We have questions, of course, on the parachute. So why is the parachute larger than the one on Perseverance, but the size-weight ratio of the payload is smaller?
Okay. The supersonic parachute on Perseverance has a diameter of 21 meters.
Mm-hmm. Which is a bit larger. Okay.
Yeah, our capsule weighs 2 tons.
Okay.
Their capsule weighs 4 tons.
Okay. Mm-hmm.
So it would have been impossible for them to land Perseverance with a single parachute on a ballistic trajectory like we use. They need to use what is called guided entry, which means that their capsule has a special shape and a special misalignment between the aerodynamic center and the center of mass that allows it to generate lift. So what they do is they fly S's, like the space shuttle at high altitude, to bleed most of their kinetic energy high above ground and then drop like a rock. That's why they only have instead of an ellipse of 100 kilometers, they have a circle of 10 kilometers.
Yeah, that offers a lot of precision in the landing.
Yes, at the cost of a much more complex flight configuration for the capsule. To give you an idea of how crazy it is, of course, when they are on cruise, they have to be mass balanced because they're spinning. Right before, and when they go into the hypersonic phase, initially they're mass balanced. When they get lower into the atmosphere, they eject like 150 kilos of tungsten on one side to make sure that the center of mass shifts. At that point, they turn on 2 sets of thrusters and they spin left and right to bank the capsule to fly the S's. But right before they open the parachutes, they need to bring the center of mass back to the center again, so eject another 150 kilos of tungsten in the opposite direction to move back the center of mass. And only then they can open the parachute. So it was used also, by the way, for Viking. So it has been known for a long time. But it's more expensive, it's more complicated, and for Exomars, we went the same way that is used for InSight or, let's say, the smaller NASA missions.
Yeah. Okay.
And as you know, we've been having all kinds of hell with the parachutes.
So, just to be clear, the problems that have been highlighted on Exomars parachutes are concerning the subsonic one?
No, we've had tears on both. The issue is the following. When the parachute comes out, it comes out at roughly 200 kilometers an hour. Well, in the case of a subsonic, even faster in the case of a supersonic. And we had problems with the design of the bags, not so much the parachutes. The bags they have pieces of Kevlar, and they had not been covered in Teflon, and so these pieces of Kevlar were cutting the canopy as it was coming out at very fast speed. So we solved those. We did a whole bunch of other tests. I mean, these tests they cost like, every time we test, it costs us about 2 million euros. We have to bring the capsule to 30 kilometers altitude, so that's the border of space, to give you an idea, and drop it from there and try to open the parachutes at the same. We cannot duplicate the speed as on Mars, but we can duplicate the dynamic load rates.
Okay.
And so we've done that a few times. We have gotten better and better, to the point that the last tests we still had cuts, but had they been like that, we would have been able to land okay. But nevertheless, we don't like our parachutes to have cuts, so we keep on testing. We're going to do other sets of drops, this time in Oregon in the US in April and May, and then again in Kiruna in Sweden in November.
No, but my question was more about why dropping in Oregon and in Kiruna?
Because of this.
Okay.
Normally, we would always drop in Europe, but it turns out that the winds are right only during certain months. So if you want to drop on months when the wind is not blowing in the right direction in Kiruna, we have to go somewhere else.
Yeah, no, I understand.
Somewhere else is Oregon in the US.
But you already foresee to have the need for 2 additional drop tests.
Yeah, and the reason is we are making changes based on the results of the last one.
Okay.
So let's assume that we still have cuts. Then we would want to test again. Right?
Yeah, I understand.
So, and let's assume it goes well. Well, okay, it went well once. Wouldn't you want to test again to be
very sure?
Right. So we thought, what the heck, we'll just buy the 2 campaigns, and hopefully the first one will be great and the second one will just be a confirmation. And if we experience any problems on the first, we still have the second one to try again.
But if the one is good and the second is bad, then you have additional problems. It's the purpose of testing, let's say.
Yeah, it tells you that your design was not robust. Then you have to understand why the second one was bad. Maybe you exceeded your Another thing is, these are qualification tests, which means that we exercise everything at loads that will be higher than what we will see during the mission.
I see. So you're over-designing a little bit.
Yeah, always.
But a question, so the postpone of the Exomars rover to 2022 was partly because of these parachute problems, or it was part of a much larger...
It was partly the parachutes. It was, I think, to the biggest extent, it was the software. We didn't have enough time, or by then we didn't have enough time to test everything. And in fact, we were still full of bugs.
Software for the rover?
Software for everything, including the lander.
Okay.
Yes, we had the software finished, and yes, we had done some tests, but when we started going into testing all the possibilities, we found that there were still things we needed to fix. So, I mean, yeah, it was a super bummer for, you can imagine, I've been working on this thing for almost 20 years. Every time that the mission has been postponed, it has been, oh my God. But the last thing you want is to lose it. So
yeah, it's better to postpone than to lose it. That's for sure. Yeah. But how did you feel about this this last postpone? Was it let's say, okay?
It was inevitable. I mean, when we knew we had problems in February of last year, and we were debating what to do, blah blah blah, when COVID hit. And by then we said, okay, guys, it's finito. There's no way. Even if we work, by then we were working on 3 shifts per day, 7 days a week. Even if we had thought of making a valiant push with the COVID situation, it became impossible.
Yeah,
so that was the last nail on the coffin. So
that means this additional 2 years in the project were actually very welcomed, I guess.
You could say fine. I mean, they're welcome in the sense that we have the chance to do a good job. But we all feel bad that we ended up in this situation.
That's for sure. Okay. I understand. That's a question from Benjamin in the chat also. Do you feel more confident than ever to launch in 2022?
Well, we still keep on finding things we need to fix, even at this late stage. What can I tell you? It's true that the problems have become less severe, well, except for the parachutes. We still need to get those. But not long ago we found that there was a DC-DC converter in one of the Russian boxes that blew, and we had to send the box back to Moscow for repairs. So yeah, it can happen.
So okay, but for now, the status. What will the rover experience for the next 2 years? So now the environment testing is still ongoing. As I understood, you will be doing RF testing soon.
So that's on the composite. So on the 12th of March, we start packing, and a bunch of Antonovs will land in Cannes, and we will put the spacecraft. It typically takes 3 to 4 flights, and take back everything to Torino.
In different pieces, not in one?
Yeah, the rover has its own container. Things fly in separate, even in separate planes.
Okay.
So what will happen is we will do some more testing in Torino, and then at a certain point the flight model of the rover stays, and the composite eventually will go to Baikonur, and the rover will go later. So we still need to do a bunch of things on the rover. We want to do a vacuum bake-out where we put the entire rover, we take off the solar panels, and then we bake at very low temperature in vacuum the rover with the bathtub open to clean the organic background in the bathtub and to flush whatever organic background we have in the ultra clean zone.
Okay.
I told you we get to see molecules of glue and other stuff that penetrate through the pressure release valve into the ultra clean zone. And even if it's still super clean, we prefer to abate the source of organics as much as possible, because now we are flashing every week or so. We flash with ultra pure argon. But during the 9 months of cruise to Mars, we are not going to be able to flash anything. So if we want to have the ultra clean zone as free of molecules as that we can detect as possible, it is important that we launch not only with the ultra clean zone, ultra clean, but also with the bathtub as clean as possible.
Yeah, I understand. Okay. So you don't really foresee any time that the rover will just wait in the corner of a room and wait for launch. It will actually undergo many testing and many activities before 2032.
No, we have what we call a storage phase.
Oh, you have? Okay.
Like 3 months, but that's in the schedule. Believe me, it will not happen. It never happens.
Yeah.
People are always working, trying to make things as good as possible until the last moment. And this will be no exception.
Perfect. Thank you so much, Jorge. We still had a couple of slides. I think just was some nice pictures of
This is just to finish. I think if you click this, the last one. I didn't mention it in the end, but the landing site is dated at 4.1 billion years of age. To give you an idea, Curiosity landed in Great Crater, that's 3.6 billion years. That's well into the time when Mars had started to dry up. In fact, the water they see is probably the last gasps of water. Perseverance is going to Jezero Crater, which is dated at 3.8, and that is the more or less the edge. It's on the dry side of this big change that I told you happened around 3.9 billion years. And at 4.1 billion years, Oxyaplanum is dead in the center of well-placed in the Noachian, so the time when there was ample water. In fact, the place where we're landing, one of the hypotheses is that it was the bottom of the Northern Ocean on the northern hemisphere, on the lowlands of Mars. So that's one of the things we want to try to prove. And why do we know that? Because the massive clays that are all over the landing site are dated at 4.1 billion years, but we also have a delta, and that delta is dated at 3.9. And for a delta to have formed at 3.9 billion years ago, it means that between 4.1 and 3.9 billion years of age, that entire place was submerged in water. And if you look at the landing site, which I'm not showing you here, between where we land and the North Pole, there is nothing that could have contained that water. So that delta basically drained into something, into a basin that had no wall all the way to the North Pole of Mars.
So it just, the water just evaporated, or just they didn't have any place to fill, actually.
No. What we think was, when the delta formed 3.9 billion years ago, all the northern hemisphere of Mars was underwater. And the part where we're landing was sort of the shallow or coastal part. mind you, Mars, the sun shone less bright 4 billion years ago than it does today. It only had like 70% the light that it has today. So it means if Mars is cold today, it was even colder then. So when we talk about oceans on Mars, you have to think more of Iceland. Very most probably they were frozen at the top, and what was keeping the bottom part liquid was all that internal heat I was telling you about, the hydrothermal systems and the volcanism.
Interesting. That could also, we could learn a lot about the Jupiter moons geology and Saturnian moons geology in that sense, right? Which are actually ocean worlds also, but
yeah, although there the source of heat is a bit different. It's mainly the tidal deformations induced by the giant planets. Another thing that is interesting, in 2012 I took a trip to Iceland, and they have this place where the government of Iceland used to meet, and every year, and it's in a very nice area where you see a lot of ancient volcanoes. And there was a geologist who was giving a little chat and explaining how the volcanoes in Iceland have a very special shape, because they actually form under glaciers. So the part that forms under the ice actually has very steep walls, and it's only the part that comes above the ice that is conical. And if you go and look at the Olympus Mons or Arsia Mons or any of the large volcanoes on Mars, you will see exactly the same shape. The terrace around the base of the volcanoes has vertical walls. And it's only the top part, so to say, that looks more like a shield volcano. They're not cone volcanoes on Mars. So it is very likely that the very ancient water on Mars would have been top frozen.
Very interesting. Super cool. Thank you so much, Jorge, for explaining everything. I'm
sorry it took so long.
No, not at all. I'm sorry for you if you stayed longer than that was agreed before, but I personally enjoyed every second of it. I really enjoyed listening. I learned so much about early Martian history, and I hope everyone here enjoyed as well. And of course, we cross fingers for the launch of Exomars in 2022. We will follow it closely, and we also follow the progress of the project until then. And yeah, thank you so much for taking the time today. And I just cannot thank you enough. And the people in the chat also. The people also are greeting you in the chat. So I think I will keep a couple of minutes to talk with the public, and I will hang up the Skype call in a few minutes. All the best for the future. If you have any last words to say for the public.
Well, I'll say, remember that after Perseverance and Exomars comes Mars sample return, and we think Exomars is well placed to try to demonstrate that perhaps we may see better quality organic molecules at depth, or in samples collected at depth. So even though this first Mars sample return mission is going to return the samples cached by Perseverance, which are in essence shallow depth samples, the results of Exomars could help us for future Mars sample return missions.
Okay, so you mean the Exomars could prove that we need a Mars sample return mission of deeper depth samples, right?
Could be.
Okay. And the last, just before we go, we have a last drawing. I'll send it to you. and I'll show it on the chat in just a minute. Let me just show it on the screen.
I cannot read the text.
You can click on it, maybe.
Yeah, it's true. Oh, now I can.
Here we go. Small slide. Okay. So let me discover it. It's been 9 days since Sophia has started the simulation. Sorry, I can't see it really well. Causality. There is no escape from it. We are forever slave to it. Very nice, Loiseau. Thank you so much. Ref à Lambert Wilson in Matrix. Okay, I don't have the ref because Matrix, I did watch Matrix so long ago, so I don't have the ref, but I love the drawing anyway. Thank you so much for the drawing, Loiseau. And Jorge, thank you so much again for being here tonight, and congratulations for the awesome project work and beautiful science we will gather from ExoMars mission. I hope the best for the mission and for you. And I hope to see you again in the future soon.
Okay, thank you so much, Corentin. I like this very much. Thank you for the great questions, and thank you so much for all your interest in ExoMars. It's really important to us to know that, we're not doing this only for the scientists that work in the mission. We're doing it for everybody, and we hope that the results and the images we will take, you will find as great as I'm sure we will.
I'm sure we will. And who knows? Maybe we'll chat again a bit after ExoMars lands. So we have a couple of discussions around the pictures and the first results. That would be so nice to have a follow-up, but yeah, we'll keep an eye on the mission for sure. We'll keep following, and in the meantime, thank you so much again, and have a great evening, Jorge.
Okay.
See you soon. Bye bye.
Bye bye, everybody.
Okay, here we go. Go back to the chat. Thank you so much, guys. I don't know if we have still English speakers here, or if I can switch back to French. I don't know. Thanks so much for podcast listeners. Thank you so much for you, YouTube. If you have stayed until now, feel free to like, comment. I'm a true YouTuber right now. Like, comment, subscribe, share it on the social media. And see you next time. Bye bye, YouTube.